In section 1.6, we're going to review exponential and logarithmic functions. We'll start by looking at the exponential ones. So these are functions of the form f of x equals b to the x, where the base has to be greater than 0 and also different from 1. Generally speaking, exponential graphs come in kind of two different types. You have the type where the base is bigger than 1, which would kind of look like this. So this would be indicative. This would be very similar to like the graph of, let's say, like 2 to the x, 3 to the x. Even the natural exponential e to the x would have a graph that would look like this first type. Okay. Very important thing to consider for these types of graphs is they approach y equals to 0 as x approaches negative infinity, and they will approach positive infinity as x approaches positive infinity. And they also have the y-intercept 0, 1. The reason for that is if you take any base, raise it to the 0 power, we get the value 1. The second type of exponential graph that's formed is what happens when the base is between 0 and 1. So things like, 1/2 to the x power, or maybe 1/10 raised to the x. Then the graph opens up and it looks like this. When x approaches negative infinity, the graph approaches positive infinity. And when x approaches positive infinity, then the graph approaches y equals to 0, which is the horizontal asymptote. So two types of exponential functions based upon the size of the base. Type 1 is the ones that have a base bigger than 1, and they open up like this. If the base is between 0 and 1, then they open up like that. The inverse function of an exponential is the logarithmic function. We write y, or f of x, equals to log base b of x. It's equivalent to the following exponential expression, b to the y equals x. So generally, whenever you see a logarithm, realistically what a logarithm is, it's an exponent. And in this statement, there's three key things that are at play here. The first thing is the base of the logarithm, which is usually written directly below it as a subscript. The second thing is what's inside of the logarithm. That's the value. And then on the right-hand side, what the logarithm is actually equal to is an exponent. When we say y equals log base b of x, that means that when you take the base b and raise it to the exponent of y, that's giving us the value x. Much like how there are two different graphs for exponential functions, there are two different types of base exponential functions. For example, when the base is bigger than 1, so things like log base 2 of x, or even the classic natural log of x, which would be log base e, the graph looks like this. This graph can be obtained if you remember relationships between graphs of functions and their inverses. The graph of a function and its inverse are symmetric with respect to the line y equals to x. This graph above, this would have been our standard b to the x graph. Its inverse is going to be the function log base b of x. So if you simply take this graph and reflect it across the line y equals to x, what you would get would be this graph here, which is the logarithm graph. So for a logarithm where the base is bigger than 1, the graph looks like this. On the other hand, if you have the graph of a logarithm and the base is between 0 and 1, so let's say like log base half x or log base 0.3x, etc., then the graph is going to look like this. From the graph, you can kind of glisten some of the key characteristics of the logarithm graph. A couple of things you would want to know is that, first of all, it has the x-intercept 1, 0. The reason for this is if you look at log base b of 1, you're essentially asking this question. What exponent or what power do I have to raise b to in order to get the value 1. And well, we know that anything to the 0 power is 1. So log base b of 1 is going to be equal to 0. So that produces the x-intercept 1, 0 on the graph. We would also want to notice that the domain is strictly from 0 to positive infinity. And then the range will be from negative infinity to positive infinity. And that doesn't matter which of the two types you have. Whether you have the first type of base graph or the second log base b graph, they all have that same common characteristics. Domain is from 0 to infinity. Range is from negative infinity to positive infinity. A couple relationships and properties of logarithms. First of all, we did mention that the function, going back, f of x equals b to the x, the inverse of an exponential function is a logarithm function of the same base. So its inverse would be log base b of x. And this statement here is nothing more than the functional relationship between the composition of a function and its inverse. If you compose log base b with the b to the x function, that will give us x. And also, if you take the exponential function b and compose it with log base b of x, that's also going to give us x. So this here is just the formal statement that b to the x and log base b to the x are inverses. Amongst all logarithm functions and also amongst all exponential functions, there's one in particular that's very convenient, and that's the one that has the natural base e. If you remember this natural number, it's approximately about 2.71828. It's an irrational number, much like what pi is, in that it doesn't stop, it doesn't repeat itself. And from that, we can use that as a base for an exponential, or we could use it as a base, I'll just call it g here, for a logarithm. Ln of x is technically log base e of x. These are two very popular functions we use a lot here. If you look at the ln of 1, just as it would be for any log base b of 1 is always 0. The ln of e, what exponent would you have to raise e to get e to the first? Well, that's just 1. And then this is kind of a subcase of the one we just saw a moment ago. Again, this is just the composition that shows that the functions e to the x and the function ln of x are inverses of each other. You can compose them in any order, and you get the original output. You get the original input x as your output. The last thing we're going to review is that there's 3 properties, there are 3 rules for logarithms. They're going to be very, very important later on in the class. They allow us to kind of rewrite things and make the calculus material a little bit easier. The first one is what's called the product rule for logarithms. And that is that if you have the logarithm of a product, we can split that apart and make that the sum of the individual logs of the values on the inside. So log base b of m times n is equal to log base b of m plus log base b of n. We have a quotient rule which says if you have the logarithm of a quotient, then that can be rewritten as the difference of the logarithms. So log base b of m divided by n is equal to log base b of m minus log base b of n. We have one more rule which is called the power rule. If you have log base b of something being raised to a power, then essentially you can bring that power out in front as a multiplication. So log base b of m to the p is going to be p times log base p of m. In example 3, they ask us to use properties of logarithms to expand each expression. And when we're expanding, that's kind of taking a single log and breaking it apart into multiple pieces. Okay. To do this, let's kind of go through and highlight each step. First thing we would notice is we have log base b of x squared times the square root of y. That's a product. So according to the product rule, this would be log base b of the first term plus log base b of that second factor. square root of y. The next thing we can do is we can actually use the power rule for each of these. Thinking of the square root of y, remember this is equivalent to the fractional power 1/2. So we can now take those exponents and bring them out in front. This is going to be equal to 2 log base b of x plus, bring that out in front, 1/2 log base b of y. And now we've successfully expanded the logarithm. Starting with a single logarithm term, we've now broken it apart into several individual pieces. Let's take a look at the next one. We have log base 6 of this quotient. Because we have a fraction on the inside, the quotient rule says that this is going to be equal to the log of the numerator subtracting the log of the denominator. So that's applying the quotient rule. The next thing we'll notice is that this expression here, 36y to the fourth, technically that's the product. That's the multiplication of 36 with y to the fourth. So we can split that apart by using the product rule. Now let's be a little bit careful because this thing is going to be subtracted. So if I split it apart into two pieces, which we're going to do, we need to make sure that we're subtracting both of those pieces. So let's kind of go ahead now and distribute that negative sign in. We have log base 6 of the cube root of x minus log base 6 of 36 minus log base 6 of y to the fourth. And then from here, we can do the power rule on the first and last term. The cube root is the same thing as the 1/3 power. So we can rewrite this as 1/3 log base 6 of x minus, this thing here is a value we can actually compute. Log base 6 of 36 represents the exponent that you would need to raise 6 to in order to get the value 36. Well, because 6 squared is 36, then log base 6 of 36 is going to be equal to 2. It's that exponent. And then minus here, we can use the power rule, the quotient rule, power rule. Bring that 4 out in front as 4 times log base 6 of y. So there you have it. We've used the properties of logarithms to expand that expression. In example 4, we're going to go in the reverse direction. Usually the directions would be of the phrase condense or try to write everything as a single logarithm. So we're simply going to go ahead and reverse our steps. If you have any fractions, or any coefficients out in front, begin by bringing them into the logarithm as an exponent. This would give us log of x to the 1/2 power plus log of the quantity x minus 1 to the fourth. And now we have the sum of two logarithms. We can rewrite it using the product rule, which says that we can make it a single logarithm if we take the product of the insides. So this is x to the 1/2 times x minus 1 to the fourth power. And that's it. If you wanted to, you don't have to do this. You could write it as a square root of x. But that's all we wanted. We've now condensed it. And instead of having several log terms like we started with, we now have condensed it into a single logarithm. Let's take a look at the last one. Here we want to, again, condense this. The first step is going to be to bring all of these powers into the exponent. This would give us the ln of x to the fourth minus the ln of, 6 squared, that's 36, minus the ln of y to the 1/2 power. From here, we're going to work our way left to right, kind of like order of operations. With these first two, I can apply the quotient rule. The difference of the two logarithms is going to be the quotient. It's the first value divided by the second value, all inside of a single logarithm. And now we can apply the quotient rule one more time. This is going to be the ln of x to the fourth over 36 divided by y to the 1/2. A little bit of fraction arithmetic, good old school keep, change, flip. And we would get the following. The ln of x to the fourth divided by 36 y to the 1/2. And now we've written it as a single logarithm.